questions about the homework? Well, they're not hard if you follow along in class from this one. So, yep. There were some three-port systems, right? Which one?
That was 10.29.
All right, hold on. 10.29, go ahead.
So here's the scattering matrix. It's 0.6.
Is it 1.6?
0.
Over this way?
Yeah.
S12 0.
J 0.8.
J 0.8.
And then it's 0, J1.
In the middle?
Yeah. And then 0.
Okay.
And then J 0.8. 0, 0.6.
Okay. That's a three-port. What do they ask?
Is it reciprocal? Is it lossless? And determine the return loss at port 1 and ports 2 and 3 are connected together.
All right. First part is it a reciprocal network, right? So for reciprocal, and I'm not going to test on that. What does it say? You have to take S, right, times S transpose, and that should be the unitary. You know what? They were this. I don't worry about this, but reciprocal network means that the parameters are the same looking forward or backward. You can flip it. And this is on page 20. Well, really, so I'm sorry, S transpose equals S. So you would get, I believe what I said. So actually what we have to do is see, I said this is really losses. If S is equal to S transpose, so does everybody know what a transpose is? If I just say S is equal to A, B, C, and D, then S transpose is simply, you're going to take these two terms, it'll still be AD, but then it'll be BC. You all remember that? Transpose is just inverting across diagonal. So if that's S transpose is going to be equal to, leave the diagonal alone, so I have 0.6, J1, 0.6, and then I flip it, and this is still J8, 0.8, J 0.8, and then 0, 0, and 0. So in fact it is. So it is reciprocal, right? It checks that, it is reciprocal. Part B is it losses. I don't usually ask this question, but so if it's lossless, if I take to see if it's lossless, it means S transpose times S conjugate should be just the actual unitary matrix, 1, 1, 1, and then 0, 0, 0, 0, 0, 0. So it just should have ones on the diagonal. And this is equation 1026 on page 563. So the transpose I've got there, it's 0.6 and 0, J is 0.8. This is J1 in the center, and this is 0.6. 0, J, 0.8, 0, and 0. That's S transpose. Now, the only thing S conjugate is going to do is take any of these J terms, and if it's plus J, it becomes minus J. Do y'all follow me what a conjugate is? So I'm going to go ahead and take this, and it's still going to be 0.6 here, 0, but now this is minus J 0.6. This is 0, this is going to be minus J1, this is still 0, this is going to be minus J 0.8, 0, and 0.6. So now gotta see if we get the unitary when we do this. So, you all remember how it is, it's row column, right? If you're gonna do this, when I'm filling the matrix out, I'll make it big. The 1-1 term is row column. You all remember how to do this from linear algebra. So I got 0.6 times 0.6, and then I got 0 times 0, and I have J8 minus J.8. So 0.6 and 0.6 multiplied together is 0.36, right? And then I have 0.8 times 0.8 is 0.64, J times J is minus 1, with the minus is plus 1, so it's plus 0.64 here, and that is exactly 1. Whitworth made this problem out, so it's going to turn out to be. In fact, you're going to get the unitary matrix, there's going to be losses. So that's 1. This is 1, yes, 1, 1. Now, the next, we could go down and fill a whole column, but next when you go over here, take a look at this. If I go, remember, if I want the 1, 2, I would take row, column. You all follow me on this? So row is going to be 0.6 times 0 plus 0 times minus J1 plus J.8 times 0, which is 0. So this is going to be 0. Next one, row, column. I get minus J.6, so it's minus J.36, and then I have, where's that? Row, column.
That top right entry in the second matrix should be minus J 0.8. Shouldn't it?
Yeah, up here?
Yeah.
You're right, you're right. So that's gonna be, minus J.48, 0, and plus J.48 goes to 0, thank you. Then down here, we can keep going, but I'm gonna tell you, it's gonna be 0, 0. That middle term, that's this times this, so it's gonna be J1 times minus J1. J times J is minus, with a minus sign is plus, 1 times 1 is 1. And in fact, if you do this, and the final one down there in the corner, if we take this times this, we're going to get plus J.64, because this J times minus J will end up being 1. 0.8 times 0.8 is 0.64, and then I get 0.36, which is exactly 1 as well. So in fact, it is lossless. But it's the row column business. Do y'all remember doing this stuff in linear algebra? Frankly, I think your calculators, and I might be mistaken, but I think you can put in a matrix and multiply it by another matrix.
Pretty much, yeah.
Anyway, that's what he's just getting at. He's just making sure that you're aware of that. Finally, let me leave that up there and tie the ports together. So this is the interesting one here. So these are the S parameters. And therefore, when I look at this, I have V1 minus is equal to S, I'm gonna write it out first, S11 V1 plus S12 V2 plus S13 V3 plus, and then V2 minus is equal to S21 times V1 plus S22 V2 plus S23 V3 plus, and V3 minus is equal to S31 V1 plus S32 V2 plus S33 V3 plus. I'm just putting them all down there so everybody sees what I'm going to be doing next. Do y'all agree with that, class? That's the matrix. And now I'm not written in a block form, I've just literally shown the 3 equations. So now I go and I change things before I do the actual connections. I got S11 is 0.6, so this is 0.6 here. I got 0 for S12, so this term goes away. And then I have S13 is J.8, so it's plus J 0.8 right here times V3. for this one, this term goes away, this term goes away, and S22 is J1. And this one's 0.8, J.8. This is 0, and J.6, or just 0.6. And that's V3. Next, he says that we're going to tie some ports together. This is a pretty big problem. So if I have this, I've got port 1 right here, and I'll do it this way. It's not a circulator, but I'll make it look like a circulator. This is port 1, port 2, and this is port 3. And he says something about port 2 and 3 are tied together by?
Determine the return loss at port 1 if ports 2 and 3 are connected together by a matched T line of electrical length 45 degrees.
All right. So he's saying that there's, across this, there's 45 degrees of change. So there's going to be a, I'll just call it J pi over 4 of change here. There's going to be e to the J pi over 4 of phase change over this plane. So next, you can equate what's going on here. Remember, for port 2, you're going to have an incoming waveform here, which is going to be V2 plus, and you're going to have an outgoing waveform, which is V2 minus, and I'll make that a little neater, V2 plus, and going in and outgoing is V2 minus. Here, you're going to have incoming is V3 plus, and outgoing is V3 minus. Y'all follow me? Now you can see what happens next. Now we're going to equate V3 minus to V2 plus. Y'all with me? Now anytime you have phase change, here's what happens. If I just have a length of line, and it's got so much phase change, say it's e to the j pi over 4 phase change, and you can put it in degrees if you want, e to the j 45 degrees. That means whatever the voltage is here, if it's called V1 plus, by the time it gets to this point, it's going to be V1 plus times e to the minus j 45 degrees. It will be reduced by that much. There's that much phase change. Y'all follow? It's not advanced, it's going to be subtracted from whatever you are here, 45 degrees less. Y'all follow me on this? And you understand the concept. So, when you look at this, you can make, and I think he does it this way. Does he work in degrees or does he work in gradients when he does this?
Degrees.
All right, if he's doing degrees, then I can take a look at V2 plus. V2 plus is equal to V3 minus, right? V3 minus times e to the minus j 45 degrees. I'm not sure if he does it exactly this way, but you can see that V2 plus, where it comes in here, is this waveform coming out, port 3, with a delay of 45 degrees. Then you can see V3 plus coming here is going to be V2 minus times e to the minus j 45 degrees. Y'all with me? Now, if you've got that, and let's see here. So I've got V1, leave it alone. Now I have, I've got V2 plus, it's V3 minus, so V2 plus here is V3 minus times e to the minus j 45 degrees. So I can do this. And
have V3 plus. I think this will do it. So I got V3 plus here, and I'm just gonna make that V2 minus times e to the minus j 45 degrees. Then when I look at this,
Wait, how'd you get the V3 again?
right here,
Yeah.
well, I take a look, V3 plus is what's coming. So I say whatever's coming out there is gonna come in here and be delayed by 45 degrees. So if I have it at that point, then I have V2 minus is equal to this. I'm gonna try to do it right here. So I have V3 minus is equal to J 0.8 V1 plus. And then I come over here, it's plus 0.6 times e to the minus j 45 degrees, and V2 minus, which is going to be this, J1, this is going to get interesting, times e to the minus j 45 degrees, times V3 minus. Now the reason I did this is, now I have V3 minus in terms of V1 plus. Do y'all follow me on this? And I also have, now I'm going to do it this way. So if I have these two together, it's really e to the minus j 45 degrees. Do y'all follow me? This time this would be e to the minus j 90, correct, class? I did e to the minus j 45, e to the minus j 45. It's going to be e to the minus j 90, which is just minus j. Do you all agree with that? If you have e to the minus j 90 degrees, that's just minus j. And the way you always think about this, whenever you have e to something, this is the angle. The length of this is 1. This would be the j-axis minus j and real axis. So e to the j0 is 1, e to the j 90 degrees is j, e to the j 180 degrees is minus 1, e to the j minus 90 is minus j. So you come over here, now I have minus j times plus j, so j times j is minus 1, but the minus is 1, so all this stuff goes away. That's what I'm gonna get at. All that goes away. And I have this, so I have V3 minus right here. I have 0.6 over here. 0.6 times V3 minus is equal to V3 minus over here. I take that over here, so I have 0.4 V3 minus is equal to J 0.8 V1 plus. And at that point, so if I divide this by 0.4, it's probably a quicker way to do this. So that's V3 minus, let's equal to that. Really what I should be doing is working on that one. So V3 plus, I'm doing this top equation here. V3 plus, V1 plus, and now I need V3 plus in terms of V1 plus, so I got V3 plus. That. this is the equation I need. I need it in terms of V3 plus. These are the two equations, the couplers. And now, I need to get V, see, this top equation has to be just V1 plus on this side. And that's V3 plus.
Okay, yeah, so then you can plug in what you have for V3 plus down there.
But that's V2 minus, V3 plus,
No, what you just calculated, no.
it's V3 minus.
Oh, I'm sorry.
But, if I put in V2 minus, right there, V2 minus. All right, we can do it this way. This is gonna be kind of an odd way. I'm gonna start with this one. I see V3 minus, I'm gonna go right here, kind of messy, but forgive me. And I'm just replacing that V3 plus here with V2 minus. And it's times e to the minus j 45 degrees. So now I've got it in terms of V2 minus. Then I look at V2 minus, and that's equal to J1 V3 minus e to the minus 45 degrees. So I'm gonna put the J.8 out here. And then I'm gonna put for V2 minus, I'm gonna put J1 times the minus J45 degrees here times V3 minus. And then for V3 minus, I'm gonna put this in. A lot of this is gonna cancel. So for V3 minus, right here, I'm gonna get rid of this e to the minus J45 times e to the minus J45 is either minus J90 or minus J times J is just 1. So all this stuff right there becomes 1. And then V3 minus is this. It's gonna be that times J0.8 right here over 0.4. It's going to be times V1 plus. Now we got the equation. Y'all follow me? It's just manipulating these things so you get one equation with both V1 minus and V1 plus. I'm going to get rid of these lower two, just so you can see it clearly. Now, I'll go through and do this. So I have J times J is minus 1. 0.8 times 0.8 is 0.64 divided by 0.4. 0.64 by 0.4 is 0.2, just like 2 is 0.16, right? So it's minus 0.16. Times V1 plus, or V1 minus over V1 plus, the reflection coefficient will be 0.6 minus 0.16. And is that the right answer, Bob?
When you did the 0.8 times 0.8 over 0.4, that's 1.6.
Oh. So this would be minus 1.6?
Yeah, and then that's right here.
And that's equal to minus 1, it looks like.
Yeah.
And that's the right answer? But it's manipulating those things, and I'll tell you, these things, the first couple of times you do them, you get a little confusing, but you're always after one thing. You want one equation that has V1 plus, V1 minus, if you're going to do the reflection coefficient at any point, or V2 minus, V2 plus, or V3 minus, V3 plus, if you're getting a reflection coefficient at one of those ports. Do y'all follow me? And you just gotta manipulate it. That's the key right there to link what's coming out of one port to what's going into another. It gets to be a little bit of a hassle, but you can figure it out. That's a pretty good problem. Do you have another question? The other S parameter ones, where they have either capacitors or resistor networks inserted, that's just finding the transmission coefficient, reflection coefficient at each port, and then using revision. voltage division to get the final output for S21 or S12 parameters. All right, so next. If there are no other questions, I'm sorry that took so long. I didn't mean to have it run that long. We're gonna do shift in a reference plane, and this is on page 566. Now, you're not gonna have a problem seeing it. I don't believe it. I think I mentioned my air conditioning is out. Well. They're looking for something called Freon 22 that apparently is being phased out. They couldn't find it, or at least they didn't get back to me. So it was another fun night last night. Sweltering at 81 degrees. I don't know how they live in the South down there. Okay, so now shifting the reference plane on the bottom page 566. So here's the deal. In general, we'll just do it with 2-port, but we can do it to N-port. If you have S parameters here, S11, S12, S21, and S22, those are magnitude and phase usually, and it's at a given frequency. You have this. Now, if we measure the S parameters here, right at the port, but we want to extend it and say we don't want the S parameters for that port, we want the S parameters for something where we're going to have a length of line L1 here, and another length of line L2 here. And we're going to assume these are matched, so this is going to be Z0 and Z0 here. And now I want the S parameters for this network, this entire network. So now I want the shifted S parameters, and I'll call it S reference, we'll call it that. So how to get them? All right. Well, remember, now my signal V1 plus is coming in at this port, and my signal V2 plus is coming in at this port. And there's a certain amount of phase delay before they get here. Do y'all follow me on this, class? So when I look at this, the amount of phase delay here is going to be e to the minus j beta, and I'm just going to call it beta times L1. Does that make sense? If this is V1 plus, the actual voltage that enters here is going to be V1 plus times e to the minus j beta L1, because we're in the frequency domain. It's just how much phase did it change, and it lost, basically. Figure it out. Follow me? Now here, the phase change here is going to be e to the minus j beta times L2. And you can almost guess what I'm going to do. When I actually look, first we'll start with the reflection coefficient. When I look at the new S11, I'll call it S11, and I'll just prime it. Now that's going to be, if you think about it, V1 plus comes in here, it comes down and hits here. So now I have, it's going to be V1 plus times the phase shift e to the minus j beta L1 times S11, because that is the reflection coefficient that port 2 is matched, right? And then it's going to come back, so you're going to get a total phase change of e to the minus j 2 beta L1 by the time the wave reflects here. All right, think of it. V1 plus now comes in here, goes down, so now there's a delay of e to the minus j beta L1 to this point. It hits, and if the reflected field is going to be S11 times that, comes back over here, and then, so now the reflected field, my V1 minus right here, is going to be phase delayed by e to the minus j 2, e to the minus j 2 beta L1. So this is really, S11 is going to be S the original S11 times e to the minus j 2 beta 1 L, or beta L1, pardon, L1. That makes sense to everybody? I mean, do you all get this? It's just one of these things where there's phase delay now, because now I'm getting the S parameters for this system at these port right here, with the shifted reference point. What do you think happens to S22? Well, same thing as S11, right? Here, I send in my V2 at this port right here. This is a shifted reference plane. It comes in, it gets a phase change of e to the minus j beta L2. It hits, right? Then it's V2 plus times S22, right? Comes back up, a second phase, just add this thing as the first, and I get simply S22 parameters times e to the minus j 2 beta L2. So that would be for the reflection coefficients in a match system, we're assuming, yeah.
And the two's because it comes back.
Yeah, it goes down with this much phase change, right? Then you hit here, so V1, V2 plus is coming down, gets this much phase change before it hits. Now the reflected field is gonna be that times S22, right? And then that has another phase, so the total is twice that. Now when you look at S21 or S12, a shifted plane, come over here and just think about it. Normally, for right here, V1 plus, right, times S21, right, is going to be V2 minus. Do y'all follow me on that? That's what's coming out of the port. But now, what's coming into the port, if I start here, here's V1 plus, I get phase change e to the minus j beta L1, right? Then I multiply this by S21. Now that wave's coming out here, but it has an additional phase of e to the minus j beta L2 added on. So the net amount of phase change is going to be, it'll still be S21, but then it's going to be e to the minus j beta, and it's going to be L1 plus L2. And the same with S12, the other direction. It's going to be the original S12 times e to the minus j beta, and it's going to be L1 plus L2. So it'll be the same amount of phase difference, phase change, as S21 and S12, because it's going total distance. Now he shows this, if you look at the matrix in 1035 on page 566. And that's really something you have to appreciate in terms of measurements, because here's one of the things I did in some experience. So one of the things long ago, I got involved with some genetic algorithms, but I used them, these are global optimization algorithms that are in a probabilistic sense, they're global. There's a good chance that you're going to get a global minimum for whatever values, or maximum, depending on how long you run the program and how many different, I guess, initial guesses you have. But here's the deal. We had something where we had 3 layers of material that were in a waveguide. So just think of a waveguide, and you got 3 different thicknesses of material, or 3 different layers of material, unknown values. This has to do with something called an inverse problem. And we didn't know the exact thicknesses, and we didn't know the electrical parameters. Do you all follow me on that? So you write an equation for the S parameters, but we had to use a shifted reference point, because we got our equipment, our network analyzer with cabling that's longer. So the length of the cable you have to work into, right? Now you'll notice these values of beta here. Beta is 2 pi over lambda. Follow? It's not a constant for all frequencies. Beta changes with frequencies. And what we did is, we got the S parameters for this system, and we measured it over a swath of frequencies, a large, I don't remember what the frequency range was, say from 8 to 12 gigahertz over X band. So we have all this information about the dial, basically the S parameters. Now, based on that, we know how to write the equation for transmission and reflection, assuming we knew what the epsilon value was. Follow me on this? You can do this. So we had these equations. And then what we had to do is use this genetic algorithm, which basically is this. It goes ahead and it takes initial guesses of of what the values of epsilon are, and it sees how close the output is from those guesses to the actual output. And then it creates a new set of guesses of epsilon based on the difference in what actually was obtained and what we guessed, or I should say, the difference in the S parameters. This is not really, it's probably won't be that clear, but anyway, based on that, then it creates another set of guesses, and it did the whole thing. So when we did this, we ran this thing, we had our S parameters, we created this genetic algorithm. A guy named Dan Fairclough was my PhD student at the time, and he worked on that genetic algorithm, and we got it down, and we extracted the exact values. Now, the reason that's important is a lot of times when you're investigating electronic stuff, this is only for 3 layers, but it could be for n layers, you don't really know what, when you did device processing, what actually happened to the material. And the minute you start actually going in and do destructive engineering, you can actually change the properties in doing so. In other words, if you start slicing the thing up and you want to take it to for a scanning electron microscope graph or something like this, then you can destroy what was actually there. So you don't know what's there. But if you do it with these non-destructive techniques, and this is the S parameter measurement, then if you can back out the electronic properties, now you know what they are without destructive testing. It becomes valuable for future engineering work. And I'm going to leave it at that for now. Anyway, that was my experience. We had to use a shifted reference plane. And that shift in phase is a function of frequency. Remember that. That beta changes with frequency. So the electrical length and phase will change. It may go from maybe 30 degrees up to 80 degrees of phase change over a select frequency band. All right. That's phase shift. Next thing is circulators. Now, circulators are real important when you have things called transceivers. If you're going to use an antenna for transmission and reception, like you do in radar all the time, then you have to have something that will quickly change the actual electrical connectivity of the antenna to the system, because if you don't, then you'll destroy all sorts of electronic equipment. If you try to listen when you're transmitting, you'll blow up that unit. So here's the deal with a circulator. Just follow me on this. And by the way, they don't have to be just 3 ports. Circulators, you can have as many ports as you want. But here's the deal. We have port 1 here. And you can say these are all xenon. Here's port 2. And here's port 3. Now, the goal of this is anything that comes into port 1, I want to come out port 2. Y'all follow me? So anything that goes in port 1 comes out port 2. Nothing goes into port 3. And there's no reflection at port 1, no reflective losses. By the same token, anything that comes in port 2, I want to come out port 3. Anything into port 2 comes out port 3. And the reflection coefficient at port 2 is going to be 0. So nothing's reflected, ideally. And then everything into port 3 comes out port 1. That's the idea. Y'all follow me on this? Now, first of all, if I write down the equation, remember for the S parameter matrix of this, what we're going to have is some. I'm going to have S11 here. I'm going to just write it down. Then S21 and S31. S12, S22, S32, and then S13, S23, S33. Okay. There's where we start. Now, I said that I want no reflection coefficients other than 0. I want anything into port 1 gets through, nothing's reflected. Y'all follow me on that? I said anything into port 2 is not reflected, and anything into port 3 has no reflection. It means these diagonal terms right here, these are reflection coefficients at the port are all 0. So you can go ahead and make them all 0 for a circulator. And it should make sense. No reflection, no S11, no S22, no S23, or S33. Y'all follow me? Now the next thing I said is everything into port 1 comes out port 2. And if you think about this, if I have V2 minus, it's equal to what? S21 times V1 plus, isn't it? Y'all follow me? I mean, there are other terms, but if this is the only one of significance, then I said everything in port 1 comes out port 2 means S21 is 1. So I'm just gonna erase that and make it 1. Next, for port 2 and 3, I said V3 minus is equal to, and this would be S32 V2 plus. Y'all follow me on this? What I'm doing here? V2 plus is the incoming signal here, right? And all of that's coming out port 2, so it's going to be passed through V3 minus. That means that S32 right here has to be 1. Y'all follow me? I'm getting it. Everything in the port 2 comes out port 3 means S32 has to be equal to 1. So S32 is 1. Next, finally, everything into port 3 comes out port 1, right? Y'all follow me? So what's that? Well, V1 minus would be equal to, come on, S13 V3 plus. Y'all follow me on this? Right? So V3 plus times S13 is V1 minus, so S13 up here is 1. Now if you look, there's no other, nothing that coming into port 1 is going to come out port 3. Nothing coming into port 3 is coming out port 2. Y'all follow me? So all the other terms are going to be 0. You can check 1, 2, 3 are 0. And that's a standard circulator in a nutshell, and I think he shows this, trying to get his page number on this. He shows this on page 569. And actually on equation 10.36 is what I put up there, I believe. Yeah, that's it. And that's a standard circulator, a standard 3-port circulator. Now, how is it used? Here's how it's used. So I have an antenna, all right? Now here, I'm gonna have my antenna is gonna be on port 2, just listen, all right? So port 2's got an antenna out here, a radar antenna, just think of it connected in there as such. And this is gonna both transmit and receive signals. So over here is my transmitter. So I go ahead and I transmit a pulse. Everything coming in goes in here, there's my antenna, that's fine. I stop transmission and I start listening. As I'm listening, anything reflected back comes out this port. When it comes out this port, it goes and it's recorded, digitized, goes from A to D, and then stored. Then it does it again. But this circulator allows it to happen. A good question you're probably thinking is, how do you build that thing? Well, it's built with materials that are magnetic, and it's a little more complicated we can get into today, but what they do is they have unique materials that will, boy, this is not the way I'd like to explain it, but do you know how like a charge moving through a magnetic field bends a certain way, right? It's called, if you have a large magnetic field and you have a charge, it's gonna bend, and the force is QV cross B, right? That's how you get, V cross B is the pseudo-electric field that causes it to bend, but QV cross B is what bends it. Well, if you have a magnetized media in a waveguide situation, when you have electromagnetic energy going in one direction, it will bend one way. And if it's coming the other direction, it'll bend the other. That's how a circulator is made with these magnetic media. And it's way out of the realm of what we can talk about here intelligently. It's more of a material science problem. But remember that, they use a magnetic media to do this mainly. There's probably other ways to do it, but that's the way I'm familiar with. And it's a little more complicated than, when I was in grad school, we had a course, and I had two, and one was crystal chemistry, and the other was a guy named Leslie Cross was on the National Academy of Science taught, and it was all about how to quantize, or how to really mathematically describe the behavior, electromagnetic fields in materials, solid materials, primarily crystal materials, but other materials. And it was a very eye-opening thing about how you could actually engineer materials based on measurements and finding out what these matrices are that are called the tensors that describe the behavior of electromagnetic fields as they propagate, or even in static cases, and how things like adding a static magnetic field will change them. A lot of that's beyond this class, but I thought I'd just tell you that there's so much more to this than what I'm saying, with you're dealing with circulators and all that stuff. This is just dabbling of it. So next, after the circulator, we could do a problem, but frankly, just that knowledge of what that circulator is, these won't be exactly zero. So, and this won't be exactly one. So usually when you get measurements, they'll put these things in terms of dB. For instance, if you have a reflection coefficient of 0, in dB that would be minus infinity, right? The log of 0 is minus infinity. Well, it won't be that. You might have minus 40 dB, minus 30 dB. It won't be minus infinity. And when we talk about a forward, you might say the forward voltage gain of 1, you won't get exactly 1. I mean, that would be what? The log of 1 is 0, right? You'd have 0 dB of loss. That won't really happen. You'll get something close. And Dr. Wentworth shows in his book something he believes is a typical representation. So he says the insertion is 1 dB for a circulator, and he has a VISWAR of 1.5, and he wants the actual S parameters, and so he does get them from there. But I tell you the truth, I don't worry about dB. I mean, I may give you some problems with it. Mainly with the circulator, I always think about the the linear value of the S parameters. You can back them out from the values in dB easily. Next, 3-port dividers. This is something most of you, probably not most, but a fair number of you probably have experience with dividers. I think you call them splitters when you're dealing with cable. Has anybody ever got a splitter? In other words, you take a cable signal in, instead of having one connection out, you have two. It's called a splitter. Anytime you split a signal, you reduce the amount of power available at each port. And depending on the type of splitter, you're going to lose a certain amount of power. So what we're talking about is splitters, and this is used all the time. I mean, you probably used them when you connected cable network inside your house, and you wanted to run cable in 2 or 3 different rooms.
Like a switch kind of?
No, it's not a switch.
Well, like a networking switch, like that. The same idea as like.
No, well, it actually just takes the power in, and it divides it, but loses some power in the process. That's the standard thing. So you're going to have the same signal available on 2 cables, but it'll be at a lower voltage or power level. So we're going to go through this, and this is going to make logical sense. So if you think about it, if you just have, you want a splitter, and this is the signal incoming in this port. Call it Z0 here. And I want to split it 2 other ways. So I'm going to take this is call it V1 plus, it doesn't matter at this point what you call it. And I want to split it, so I want some of it coming out here. We're always going to assume the same piece, so this is going to be Z0. And you want some of it coming out here. And this is going to be Z0 as well. So now my primary goal is to make sure there's no reflected energy. That's the primary. Can everybody follow me on that? So how do I do it? Well, what they usually do, because it's only split it's split 2 ways. 1 way coming in, split 2 ways coming out. They're going to add a small resistor here, and a small resistor here, and then a small resistor here, and they're going to have, this will be the same ground plane, so connect there, and then up here. So they're going to have 3 resistors in this triangular fashion. Now the value of these resistances is calculated so that the input impedance right here will be Z0. Now the drawing of this is in the book, it's on page, at the bottom of page 570 if you look at it. So let me go through this with you. We're gonna talk about how to get these values. You don't even need that line there, but the only thing you need to do is understand there's three values of resistance. So if I look at this, if I just look from here that way, if I just count this, if I have R, and then I have an impedance Z naught here, I know my impedance looking here is going to be R plus Z naught. I hope you appreciate this. It's that simple. Y'all follow me? So I've got R plus Z naught. I look from here that way and I have R plus Z naught, and from here that way and I have R plus Z naught. So that means I have really R plus Z naught in parallel with R plus Z naught. Or it's really the input impedance at this point, looking that way for these two ports, is just R plus Z naught divided by 2. Make sense to everybody? So I have R plus Z naught divided by 2. If there were 3, if I had to split it 3 ways, it would be R plus Z naught divided by 3. Follow me on this, class? Because they're all in parallel, same value of R. Then I have to add this R to it, so plus R has to be equal to Z naught if I want no reflections. So now if I come over, and remember that was the point here to here, I had R plus Z naught in parallel with R plus Z naught. Impedance that way, R plus Z naught over 2. Then I add R to it, now I'm right here, but in order to get no reflection, it has to be equal to Z naught. Y'all agree? So, what is that value? When I split it 2 ways, what's the value of R? Well, let's go and just do this. We're gonna have R over 2, and R is 3/2 R. Right? Would be equal to that Z naught over 2 and Z naught on that side. Subtract that from that, that's Z naught over 2, correct? Just look at, do the math yourself. Y'all agree with this? So that means what? R is simply Z naught over 3. Y'all follow me? And that would be a resistive divider, and it's simply for a two-way splitter. So the value of resistance would be Z naught over 3. What happens if I, instead of splitting it 2 ways, I split it 3 ways? Suppose I had another port coming out here, same exact parameters. Then it would be what? At this point, at this juncture where the split takes place, I would have R plus Z naught over 3. Y'all follow me? Then you'd have to add R to it right here, and that would be equal to Z naught, and you'd get a different value for R. And it keeps going that way. Can y'all follow the thought process, class? We're gonna keep these all the same. So, that's what the value would be. Now, what are the S parameters then gonna be? And this is again for just the splitter 2 ways. It's not a circulator, it's a splitter, so we want the S parameters. So if you look at this, the first thing is S11 equals S22 equals S33, and that's 0, right? Because the goal of this thing is to make sure there's no reflected energy. That's the whole deal. And by the way, that's a very important deal. You don't ever want reflected energy. It causes nothing but problems. Reflected power. So you make sure S11, S22, and S33 are 0. Now, how do I get, this is port 2 here, and this is port 1. How do I get S21, which would be V2 minus over V1 plus? I'm going to try to draw this out for you so you see it. So if I look here, and I think about this, just I'm going to put resistors instead of Z naught there. I've got, here's my port 1. I've got a resistor here, and the value is Z naught over 3, correct? That's this value, right? Because we said we calculated that value over there. Y'all follow me? That's what R would be for when we have just a two-way split. Comes to there, and then what do I have? Well, I have basically another Z naught over 3 in parallel with a Z naught over 3, right? And then here's where I'm I'm gonna represent the transmission line as just Z naught. Down here, I'll represent the transmission line as just Z naught. Now really what I wanna get is the voltage here, which would be V2 minus, and the voltage here, which would be plus to minus V3 minus. Y'all follow me? Make sure that you see at least the logic here. I'm trying to show you this with just resistive network. So if I want the value of either V2 minus or V3 minus, how would you go about getting it? And by the way, the value of Z naught is inconsequential, so I could make this just 1/3 of an ohm, make this 1/3 of an ohm, make this 1/3, doesn't matter what Z naught is. Make this 1 ohm, make this 1 ohm. So how do you get the voltage here, V2 minus or V3 minus? Y'all see it's a simple voltage divider? I want to know what these two voltages will be with respect to V1. So here's how I do it. First, I want to find the voltage from here to here, and I'll call it V prime. So when I'm looking at V prime, what I'm looking at, I'll put it here. When I'm looking at V prime, I really have this, I have just 1/3, here's my V1 plus, and then over here, I have 2/3, right? Of an ohm, and I want this voltage right here. Everybody agree with that? So the voltage, when I look at V prime, right, that would be V1 plus times, and then it would be 2/3 over 1/3 plus 2/3, or simply 2/3 V1 plus. And that's the voltage right here. Can y'all follow me on that? Now, when I split that again, now here, I'm gonna just take it and I'm gonna say I have plus to minus V prime, which is equal to 2/3 V1 prime, or V1 plus, pardon me. And now I have a resistance here, which is 1/3, and a resistance that is 1, and I want the voltage here. I want plus to minus, and this will be either V2 minus or V3 minus. They're both going to be the same value. So that value becomes this value. Now, I just want this voltage. This is simple voltage division. I take V prime, I'm getting my free. Anyway, I'm going to take this value, V prime, and I'll just do some voltage division. So I can say that V2 minus equal to V3 minus would be equal to V prime times 1 over 1 plus 1/3, or simply V prime times 1 over 4/3, or simply 3/4 V prime. And since V prime is 2/3 V1, it's going to be 2/3 V1 plus times 3/4, and that is going to be simply 1/2 V1 prime, or V1 plus, V1 plus is going to be equal to V2 minus equal to V3 minus. So when we think about S parameters, we go ahead, we're going to start. This is going to be a 3-port, so S11, S22, S33 for this one are all 0. Then the next one I get, when I look at this, S21, which will be equal to S31, are really equal to V2 minus over V1 plus, or V3 minus over V1 plus. And if you look at that, they're 1/2. So S S21 is 1/2, and S31 is 1/2. If you take a look at that, and let's see. And since this thing's symmetric, you can also see that S12 and S13 are 1/2 as well. Just, it's symmetric. You can just take a look at this. That would be 1/2, 1/2. And I think he's going to have this. Yeah, he shows it in equation 1043. Everything else is 1/2 except the diagonal terms, and there's 0. And the reason is the symmetry of matrix. So there's no reflection. That means all that diagonals are 0. 1, 1, and 2, 2, 2, and 3, 3 are 0. Everything else has a value of 1/2 on that one. Now that was just a splitter. It was a simple splitter, okay? If it was not, if it didn't split 2 ways, if it split 3 ways, you'll have a different value for R here that you'd have to calculate. And again, all the diagonals would be 0 and everything else would be down. I think the split on it, if you split it, that's a 2-way split, 3-way split. I think these all become 1/3, but honestly, don't. It would be a 4-port device and everything would be 1/3, I think, except the diagonals. But that's with resistive division. Now, the thing you should note is you're losing power in here. If we actually calculate the power loss, you're going to see you're losing a fair amount of power here because you're using resistors to do this. You're not using capacitors and inductors to achieve this. A better way to do this for a 2-way split is with something called a Wilkinson divider, and he shows that on top of page 571. I want to just talk about that briefly because it is valuable for this. And they are used when they fabricate circuitry. Wilkinson's dividers are used. The bad part about a Wilkinson's divider is it only works for a small band of frequencies. It's designed in a way that will only work for a certain frequency, ideally, but it'll have a band of frequencies. So you can get some deviations that don't have to efficiently work. Now, that resistive network doesn't matter about the frequency. You can have it work on any frequency you want. So here's a Wilkinson divider. Wilkinson book doesn't go into detail with it. It's a splitter, I'm sorry. I guess it's called a divider. They're going to have port 1 here. And then what they're going to do is have 2 different transmission lines that are both a quarter wavelength long. You're basically going to have length of line here that's λ/4 long, and then another length of line that are λ/4 long. Now follow me, this is going to have a characteristic impedance of Z0. Coming out this port, this characteristic impedance is Z0. Coming out this port, this characteristic impedance is Z0. Y'all follow me on this class? So all the ports have the same exact load. They have Z0. Each of these are a quarter wavelength long, but the impedance of these right here, the impedance of this line right here and this line are going to be, both of these, are going to be square root of 2 times Z0. Y'all follow me on that? So now the characteristic impedance of these 2 lines that are exactly a quarter wavelength long are square root of 2 times Z0. And I think he shows it better than I'm drawing it on top of page 571 if you look there. There's one other added feature between the tops of these 2 things. There's going to be a resistor. The value of that resistor is 2 times Z0. I believe it's twice Z0 in his book. That resistor ideally will not have any current flowing through that, but it's there for a reason. Can everybody follow me on this? Now, if you wanna know how this thing works, in the book, when he discusses this, he says the analysis is a little complicated. It's not that complicated, but it's tricky. So you start by thinking this: if I have a transmission line of length lambda over 4 with a characteristic impedance of square root of 2 Z naught, and then I load it down with a load that has a load value R equals Z naught, which would be like ZL. Y'all follow? This is Z naught over 2, and I want to know what this impedance is, Zn. Y'all follow me on this? Now this is your classic transmission line. I mean, it's really the input impedance of a single transmission line is terminated into a load that's different than the characteristic impedance. This is the characteristic impedance. That's the load. So Zn, if you remember the equation, I'll just write it up, then I'll put the values in. Zn is equal to Z naught times ZL plus J Z naught times tangent of beta L over Z naught plus J ZL tangent of beta L. Y'all remember that? Okay, now, first thing, when I look at this quantity beta L, well, beta is 2 pi over lambda, and the length of our lines are lambda over 4, right? So my beta L becomes pi over 2, right? Follow this. When you think of the tangent function, I'll just draw it. If this is the argument of, if I put tan of x on the vertical axis versus x, here's at 0, but what happens? It does this. Kind of comes up, and at 90 degrees, or at pi over 2, it goes to infinity. Y'all follow me? Tangents are, and when you ever get close to 90, it's asymptotically approaching 90 degrees. What that means is this. If you look up here, these two terms will become extremely large, and then the top and bottom, the tangent functions will divide out. Do y'all follow? So we can ignore these two. And we can ignore the j's. And we can ignore the tan. So now what I have is Z naught squared over ZL. Now that's called a quarter wave transform. You can calculate the value, and this would be Zn. If you wanted the value of Zn for any ZL, you can calculate, if I take ZL times Zn, take the square root of that, that's the characteristic impedance I'd want for that line. Y'all follow me on this? Now, for our line, our Z naught is what? Square root of 2 times Z naught. Follow me? So this becomes square root of 2 times Z naught is 2 Z naught, isn't it? Because look here, that's what the characteristic impedance is of the Wilkinson's divider. The load is just Z naught, right? I just follow me on this. Z naught. So that's equal to simply, right, Z naught squared on top. This is simply equal to 2 Z naught is the input impedance to this line, right? Can y'all follow me? I mean, I started here, I mean, I had Z naught squared over ZL, right? My Z naught is square root of 2 Z naught, actually, right? So you take square root of 2 Z naught and squared, you get 2 Z naught squared. The load is Z naught, that's over here. That's what it's going into, Z naught. So I actually get 2 Z naught as the input impedance here. Just look here. And here. Can you all see that? But they're in parallel. So the net value of Z naught here, or the net value of the input impedance, is just Z naught. You all follow me? That's how Wilkinson's divider works. So it gets that. Now the reason.
Sorry, I think I lost you. So it was that Z naught over ZL, then the first.
This is Zn here would be equal to Z naught squared over ZL, right? That's after I got rid of the tan function.
So then, how'd you substitute Z naught in for ZL?
All right, what is the actual characteristic of impedance of transmission line here? It's square root of 2 times Z naught. Square that.
Yeah,
You get 2 times Z naught squared.
Yeah.
And what is ZL? well, the load is Z naught, right? So then I get two Z naught squared over Z naught, which is just two Z naught. All right, two Z naught right here, if I look at this point, and I look at this transmission line, it's two Z naught, this transmission, two Z naught, they're in parallel, it's exactly Z naught, which means the characteristic impedance I'm looking into is the same as when I'm coming from, where the reflection coefficient is 0. Now, this resistor, that what's in there, ideally you don't need it, all right? The reason is because you get imperfections, non-ideal things, and if you don't have that resistor there, then you can get all sorts of weird standing wave things that can happen. I can only tell you that much about it. I haven't, the analysis of this thing, if you do the complete analysis, it's gonna take a lot longer than that. But that's, without that resistor, that's the ideal. But you have to have that resistor because of the imperfections and things like that. It does prevent any kind of ringing. Now, you understand that anytime you have something, like you have two transmission lines, or you got transmission lines where the characteristic impedance is not the same and they're put together, that if there's any kind of a problem, any kind of an imperfection, you can get standing waves on those things, because you'll have reflections of both sides. And that's one of the reasons they do that. There's probably several others, but that's, I guess I'm out of time right now.
I'm saying that like with the splitter thing, that with the splitter thing, that if there's any kind of problem, you get the standing wave.
Well, here's the problem right here. All right. Just assume, remember, you're coming in from Z naught, then you hit right here, you have square root 2 Z naught over here.
Yeah.
All right. So if this second line wasn't here, you would have reflections, right? You would also have some reflections if it comes this way and hits this Z naught here. There's a reflection coefficient there that isn't exactly 0, right? But when I put this resistor on here, 2 R naught, then the reflection coefficient looking at this port will be 0 as well. I mean, it's a more advanced, it's more work to do that through it. I'm not sure it's worth it right now. All right, the last thing I'm gonna just mention today is when you talk about couplers, they're nothing more than something that's similar to a circulator, except now they're gonna have, with a circulator, you get ideally all the voltage coming in one port leaves the other, all the power in one port leaves the other. When you have a coupler, that he's talking about, a 4-port coupler, what he'll do is have most of the energy leave one port, like from port 1 to port 2. Some of it also, a much reduced value, will bleed over to port 3, basically for synchronization purposes. They have a 4th port that really doesn't do much, but a 4th port is a second way to monitor it, and he shows you these things in his book. I'm gonna ask you to please go through the problems I give you. Now, on Monday, I'm going to give you a quiz based on the homework I gave you up to this, like the last homework and the homework tonight, all right? There's gonna be one quiz, and that quiz is gonna take care of any missed quiz grades, or it will replace your lowest quiz score, okay? And that's, so please be here on Monday, and I'll do it at the end of class. I'll talk about the final exam 2 on Monday. This is about where we're stopped material-wise, but I wanna do some of the problems. And if you wanna know about the final, I think is it Wednesday?
It is, yeah.
Is it at 8?
Yeah.
Well, mark that in your calendar, sitting on. I'll tell you this, because I get a lot of questions. If I was you, I would go through and review the quizzes. Then review the homework, and especially areas you feel a little awkward. It's comprehensive, but the final probably have more to do with the last part of the material because we haven't had a test on it. So just realize this stuff is important. And 6 problems typically, maybe, but you know, there's multiple ones. So you get a plane wave problem, 3 or 4 questions related to a plane wave. You get something with microwave, 3 or 4 questions. You're gonna get something with antennas, 3 or 4 questions. You get something with radar, maybe 2 or 3 now. Then, you know, it breaks down that way when you get into S parameters and really L section matching, right? We did that. So, and you can bring your own rotated Smith charts if you want. I sent you some, you can print them out for yourself. But I would start studying if I was you, like this weekend. Don't wait until the night before. But if you've been keeping up, you probably won't have any problems. Most good students do great on the file, really
really exaggerated, deliberate, that you can keep, because it's not long. By the way, I enjoyed this class. I'm sorry today.